Hello everyone. This video is just a continuation on our series into statics, delving into the first moment of area using integral calculus in the college engineering statics course. For now, we're going to be looking at taking the principles we studied in the last video on centroid and combining it with a prior lesson we did in the semester for joints, joint supports, and connections to establish static equilibrium through reactive forces and moments, torques, and forces. Let's just say we have just this following practice problem. We have some ruler, some bar. To keep something simple, it goes from 0 to 1 meters. And at the 0 meter mark, that bar is connected to a pin support so that it can rotate in clockwise or counterclockwise, but only along one axis. That means that it will have potentially up to 2 reactive forces at that point. Reactive force RAY. If we're calling the pin point A, it can have a reactive force in the Y direction and a reactive force in the X direction that we're going to initially assume is in the positive Y and positive X direction. Well, in addition to that pinpoint or that pin connector, there's also a roller support on the other end of our bar that we're going to say is actually right at the very end of our ruler. And like with any roller connection, it will cause a reactive force that's perpendicular to the surface that is resting on it or that it's connected to. Since the surface in this case is connected horizontally, that reactive force is going to be pushing vertically, which we're going to assume that the reactive force at roller B, reactive force B, is going to be in the Y direction. And we usually just assume that it will be in the positive Y direction until we find out otherwise. The actual ruler itself is going to have 30 newtons of force, which if we assume that it is a uniform ruler, then that 30 newtons is going to be exactly applied at the halfway point of the ruler, which is 0.5 meters away from where we can actually have a moment or a torque. That will be called WB or W bar for the weight of the bar. And then for our special object, WSP, let's just say that that object that is resting on top of our bar can be represented by the curve f of x equaling the square root of x, and then g of x equaling 0. Well, that object is going to have a weight of 10 newtons, and if we assume that we have a uniform gravitational field applied to this free body diagram, then when we find the centroid, we will actually have the point where we have our center of gravity as well, or where all 10 newtons of that object can be assumed to be applied straight down. So let's solve for our centroid, and then use our static equilibrium equations of moment and our x and y forces to solve for our 3 unknowns: the reactive force at connection A in the y and x direction, and the reactive force at connection B in the y direction. Solving our equations for our centroid, what we're going to have is our area going from the integral 0 to 1 of our top function, the square root of x, minus our bottom function, 0. That gives us 2/3 times x is 2/3 from 0 to 1. That gives us an area of 2/3 meters. Therefore, solving for x bar, we would have 1 over the area, or 3/2, times the integral from 0 to 1 of x, times the quantity of square root of x minus, let's see, apologies for the typo, taking x bar as 3/2 times the integral from 0 to 1 of the quantity x, or x times quantity of the square root of x minus 0, dx, that gets us 3/5 times x to the 5/2 from 0 to 1, that would equal 0.6, or 3/5. If you would like to solve for the entire centroid, y bar would be 3/2, the inverse of area, multiplied by 1/2 every single time, times the integral from 0 to 1 of our top function squared minus our bottom function squared, which after we take this square root of x squared, that becomes x. So the integral of that just becomes x squared over 2 times 3/4 from our constants that were outside the integral, ranging from 0 to 1. That gets us the y-coordinate 3/8. Now, since our ruler system is actually horizontal, really all we need was the x-coordinate of our centroid. But there may be problems where you're asked to actually plot the centroid, therefore you would need both x and y coordinates. Using the information that we now have, if we just solve for the moments, the summation of moment A, in other words, the moment about our connection A, the part where it can actually rotate, well, that has to all equal 0. All the moments in our free body diagram relative to that point are going to have to equal 0 in order for us to be in static equilibrium. And before we worry about clockwise and counterclockwise, essentially that's going to be the moment of our bar plus the moment of our special curve, special structure, plus the moment of our reactive force at connection B in the y direction. The reason why reactive forces AY and AX aren't shown is because forces that are at the point of rotation cause no moment, therefore we don't need to worry about them. So essentially assuming that we're rotating at A, where we have the most unknowns, that lets us cancel them out early on as we solve for at least one of our other unknowns. Now, as we look at our forces, the 30 Newton weight of the bar would actually be rotating our structure clockwise, so we would make that negative 30 Newtons. And because it is a y force, we're going to want the x distance between that force and our point of rotation, which is 0.5 meters. The weight of our special surface, special structure, we already determined that the x-coordinate is 0.6 along this ruler. So it is a y force of 10 newtons. It has an x distance away from our point of rotation of 0.6 meters. Like the weight of the bar, the weight of our special surface is going to cause clockwise rotation. So we will make that negative. And assuming that our by is in the positive y direction, we're going to say that that is going to cause, relative to our point of rotation, a positive torque. So we'll leave that as plus. We don't know this reactive force's value in newtons, but we do know that it is the full 1 meter away from our point of rotation. And therefore, if we set that all equal to 0 and solve for RBY, that gets us to 21 newtons. The thing that's important is we're just solving for magnitude, so this should always come out positive. If it came out negative, then that just means that we were incorrect in assuming that this was an upward force, and it's actually in the opposite direction. but since our magnitude came out positive, we were correct in assuming that RBY is in the upward direction. Now then, solving our static equilibrium equations for our axes. Let's look at the summation of forces in the y direction. They all have to equal 0. And this is going to be pretty easy. Our only y forces are the reactive force in the y direction at point A, at connection A, the weight of the bar, the weight of our special surface, and the weight, or I should say the force, the reactive force of our roller connection B. Well, we're going to assume initially that RAY is in the positive y direction. We know that RBY is in the positive y direction, and both weights, they are in the negative y direction, hence the minus signs. Thus, if we rearrange everything after setting it equal to 0, RAY, reactive force at connection A's in the y direction, is 30 newtons, plus 10 newtons, minus 21 newtons, which comes out to 19 newtons. Because our magnitude is still positive, that means we're correct in assuming that RAY is in the positive y direction. So we just solved for RBY and RAY. In this particular example, we only have one potential force that's in the x direction, and since the summation of all forces in the x direction have to equal 0, our single force in the x direction, REX, happens to also equal 0 newtons as well. Now then, if you were to write your answers of your unknown forces, what I would ask you for your class is to write down all the forces and essentially write down their magnitudes, and also in parentheses you could use an arrow like an up or down or left or right arrow, or in words just write the direction of what that force would be within our free body diagram. So RAY is 90 newtons up, RAX happens to equal 0 newtons, RBY is 21 newtons in the up direction, and our only other forces are the weight of the bar, which would be 30 newtons straight down, and the weight of our special surface, which would be 10 newtons straight down. As always, a like lets me know that this content is helpful to you. A subscribe would definitely make this channel go more places than it currently is in. And a comment would just be a fun little dialogue between yourself and myself. So, while they're not necessary, a like, subscribe, and a comment will always be appreciated. In any case, I hope you have enjoyed the video, and I wish you all a very good day. And according to the time of this video, happy Thanksgiving to everyone, and any other holidays that might be happening around this time for this year. All the best, and peace.